course. I'm happy to see so many of you. Many of you will be on the video. Today I want to finish talking about multi-agent programming in Erlang. I will start by giving you a refresher, how Erlang works, the basic important concepts, especially the concept of linking, and also very quickly the gem server and some patterns to get you back into the way of thinking. And then I want to talk about supervisors, and I will show you the code, the complete code of a simple supervisor. This is really the magic of Erlang, how the supervisors will help make the behaviors reliable. And then in the second part, I will give you an industrial talk. The slides were made by an engineer from a company called Demonware, which does a lot of support for gaming systems. And this is a very comprehensive industrial talk that shows how Erlang is really used in a very complex and large industrial setting. So this is very nice. This gives you some experience how things work in the real world. Okay, so that will be the second part. So all of this stuff is not just theory, but it's really useful in practice. Okay, so first a refresher, but before that, a few seconds of respect for the Ukrainians who are fighting for their freedom and for our freedom. Okay, let me first refresh you very quickly. I'm not going to go through everything, but I will refresh you on process linking and the gen server. So let's go to the linking. This is the basic mechanism that's used to build what I called the deep magic of Erlang, which is the supervisors and the behaviors that are supervised. The basic mechanism is the linking, where two processes are linked together, and when one process terminates, a signal is sent to the other one. And this is transitive. If you link many processes, it makes a set of linked processes. And we distinguish between normal exit, everything's fine, it just terminates, no problem. The exit reason is normal, and so it could be ignored eventually. But if there is any kind of an error, a runtime error, hardware error, software error, anything that causes the process to fail, the exit reason is given and sent to all the linked processes. So I said it's transitive, and a process can also not terminate when it gets the exit signal, but it can receive it as a message, which means it can observe the failed process. And this is a really important basic mechanism. And it works because the processes are independent. Remember I said there's no sharing, there's no pointers, there's no shared memory. Each process is an independent little island. And one process can then observe the other. And this is the mechanism, this is all you need. This and the message passing is all you need to build the magic, the real strong magic of Erlang. Okay? That's one thing that I want to refresh you on. We'll go a little bit farther. So Erlang has a certain philosophy that failure should be very simple, fail fast. The number of failure modes should be very simple. Let it crash. And let me refresh your memory on the concept of a behavior. A behavior is like a programming pattern, but it's not just a discipline by the programmer. There's a software library that implements the behavior. And this is a concurrent, fault-tolerant pattern. Okay? And the Erlang, when you write an Erlang program, You don't use linking yourself. You don't actually even send messages yourself. You use the behaviors. And the Erlang platform, OTP, provides 5 behaviors that are standard, 4 that are part of the application, and the 5th one is the supervisor. That's what I want to talk about today. This one is connected to all the others. So there's a lot of very clever code behind this facade. All of these other behaviors are supervised, okay? And the 3 important ones, and it's basically almost all you need, is the generic server, the generic event handler, because events can travel in the system, and the finite state machine, generic finite state machine. So this is actually very general. Any computation is modeled as a finite state machine. So a state and an event gives you some actions and a new state. Okay, so this is the core of the computation, and then there's the 2 others are for how things are communicating, and then there's the bundling of everything into an application that can be started and stopped together, and this is the application behavior. So these 5 behaviors are really the core, and they're built on top of the simple message passing linking stuff. Okay, that's the second thing. Now I refresh your memory on what we saw last time, the generic server. I showed a very simple generic server. So let me just give you this picture first. This is generic module, so this is part of the system. Okay, this is part of OTP, the generic server, and you can use it. And this one, the specific module is what the programmer writes. Okay, so the programmer calls the server, start, stop, call, but the server has callbacks. So these 2 interfaces are part of the server. So the server interface, you start, you stop, and you call it, and the callback interface, and that's all you have to write. And the rest, the external interface, is defined by the specific module. So basically, all you have to do here is define what is the external interface and what is the actual computation. How do you initialize something? How do you actually do a computation, handle, and you terminate. So it's very easy, yeah? You start, you're working, and you stop. Okay? So this is the generic server. I showed you the code of a simple server. This is a very simple one, okay? Just to show you how you can separate this specific stuff from the generic stuff. But this one here, it does not use a supervisor. The real Gen server is supervised, okay? It's doing much more than this. Even though from the outside it still looks very simple. So this guy is doing a lot of stuff and is supervised, okay, for fault tolerance. Okay, so that's the second thing I want to refresh. Now I want to talk about 2 things, 2 little things, programming patterns, little programming things that I didn't talk about last time, to refresh also your memory on how you think how programming is done in Erlang. So here's a simple example. So message passing. You send a message from one process to another, and sometimes you wait for a reply. But sometimes it's tricky. There's hidden difficulties. You can have race conditions sometimes, and I'll show you one of the problems of message passing when you want to do call and get a reply. This is done internally by Gen server, huh? So the programmer doesn't actually have to do this. The Gen server will do this. But it's important to know how it works. Okay, so here's the problem. So I have a client and I have a server. The client sends a request to the server and gets a reply back. Okay, the client here sends a request to the server, so this is a tuple, and gets a reply back. So this is a very usual kind of pattern in Erlang. But what if there's another guy sending a message that has exactly the same form as this reply? How do we make the difference? So this is kind of a race condition, huh? You see, this one is doing request reply, but what if somebody else just sends a reply there? How can we be sure? How can we guarantee that this won't happen? You see that? Because this reply might arrive first, and then it gives a problem. Okay? So here's another one. This is sending reply, but this reply is maybe not the reply coming from the server. How can we be confident that the reply is actually coming from the server and not from somebody else? But with this code, we cannot do it. So this code is actually bad code. But we can solve this problem. We can make sure that the client, that the reply, we know it's coming from the server. Can you imagine how we do something like this? You didn't see? How would you fix that problem? How would you make sure? It's actually very easy to fix it. Okay, can you think? What would be the way of solving that? You see the problem, huh? So you somehow have to distinguish those, and the idea is kind of to make this one unique, yeah?
Set another content with a state that is only known to the client?
Yeah, something like that. So you put something in here, which is only known to the client. And that's very easy to do. You have to put some kind of a unique thing. This is sometimes called a nonce or something, a unique value. So here's the fix. Erlang has a function called MakeRef. This creates a unique constant, okay? What they call a unique reference, which cannot be forged by anyone else. Notice this is very similar to what we used, the name concept. It's basically the same idea. And the fix then is you create a unique constant, here ref. When you send the message, you send a tuple. Instead of just your own PID, you also put this unique constant in it. And the reply, this tuple has an extra field which is going to be the unique constant. That means the receive, remember how the receive works with pattern matching, it can take messages out of order, it will pick the message that has this constant. So if there's another message, here's the fake message, reply, and ref, this is just an atom, doesn't do anything, reply, it will not take this one, okay? So the receive will take the first message that matches. Notice it's very important that the receive takes any message in the mailbox out of order, okay? That lets you it doesn't matter in which order these two messages are in there, the receive will always pick the good one because of this unique constant, okay? So you see, this is one way of making the messages unique, and this works also because of the receive, that it can remove messages in a different order, okay? This technique would not work for port objects, which receive messages in the order. There you would have to do something else, okay? But this is a simple pattern that works for Erlang, and this is used all the time to guarantee that the request reply is never corrupted. It's a secure request reply. So that's a simple pattern. So you see the kind of thing when you really do multi-agent that you have to worry about. Another thing I want to talk about is synchronous and asynchronous calls. So this is very simple. And when you send a message from one process to another, sometimes you need a reply, and sometimes you don't. Okay, sometimes you have to wait for a reply, and that's called a synchronous call. And sometimes you don't. And so the gen server will give you two patterns, two interfaces, which are called call and cast. So call here is actually a round trip. It waits for a return value. If you remember the frequency allocate example we did in the gen server, we used call, okay? So notice, let me just go quickly back to the code for that. So notice when we call this is the specific module. When we call the generic module, we use call, which means we need round trip. But actually, for the deallocate, we don't actually need to get a return. It's just enough to send the message. So going back here, if you want to do an asynchronous call, sometimes you send a message but you don't expect a reply. So the gen server has another part of the interface called cast. So the idea is cast, when you cast this, you just throw something, you don't wait for a reply. Okay, so the idea is you're just sending and you're not waiting for a reply here. And the deallocate, in our example, it could have used cast actually. I showed it with call, but actually, if you want to make it more reasonable, you don't have to wait for a result, so it's used call. Okay, so that gives you back, so this kind of stuff is automatically done, the behaviors. Now let's go to building a supervisor. So first I refresh you on the supervisor concept. So the supervisor is really a key concept in Erlang. It is the concept really that makes Erlang a complete and very nice system for building robust software. Okay, so a little bit of motivation. So we're building concurrent distributed systems with failures. Most faults and errors are transient. That means if you retry, the system will work. Not all, let's say 80–90%, but the others are not. But that means if you can already handle these, you will already have a good start. So that simple retry is actually a very good strategy as the first strategy. And supervisor started out like this. And then it was elaborated, you can do much more, of course. But the basic design lets you very easily do retry. Okay? So you have a set of workers. They are supervised. So supervising means that there are processes that observe the workers, but only the failure of the workers. They don't care what the workers are doing. No? They only worry about failure. And the supervisors have authority. That means they can stop and restart. They can control the working of the supervised processes. And it's recursive, okay? The supervisors can themselves be observed, okay? So it's a tree. And the supervisor trees that are implemented, actually, it's kind of tricky to implement them if you really want to do it well, because when you start up the supervisor, you can imagine you have to start it up exactly right. Or what if there's a failure during the startup of the supervisor? So you can see it's not so simple, but no problem, no worry. This has already been done. This is implemented in the OTP, so you don't have to worry about that. This is already solved, okay? Okay, so the supervisors make a tree. You have supervisor nodes. So the root node is the top level. There is a top level supervisor and the internal nodes. So this root node, of course, is very important. If that one fails, then you're really dead, okay? So this is typically an extremely small and very well tested piece of code. So that's a very important thing, but it's usually extremely simple, this root node. And so a supervisor has child processes, and all behaviors, the four other ones, are designed from the start that they can all be supervised. So this is built into the system, okay? And when a supervisor wants to restart the workers, it has a strategy, and their basic strategies, there are 4 basic built-in strategies. One for all, rest for one, and simple one for one. So which I will explain. And the basic strategy is just to restart when there's an error. Many errors are transient. It's surprisingly effective. This is something well known by people who use Windows. If you had a Windows system has a problem, you just reboot. This is kind of a running joke for a Windows system, but it's a good strategy to restart. But you have to carefully design it. You don't want to restart forever. The number of restarts is limited, so you don't restart too fast. And the number is, if the limit is exceeded, then the supervisor will terminate, and there's a higher level supervisor that says, ooh, it's another problem, okay? So the basic retry strategy is only the first level, okay? And maybe, for example, there's a disk, and each time you reboot it, it crashes again. And this might happen once because there's a piece of dust in there, and it works, or you have to reformat or something. But then at the higher level, if something goes wrong, you might have to reconfigure the system to remove that disk. So that's something that's done at a higher level. Okay? So the supervisor has this hierarchy. So here's some example. So the squares are supervisor processes, and the circles are the workers. The workers are standard behavior. This could be Gen server. And the supervisor, so here 1 means it's a 1 for 1, and A means it's a 1 for all. I'll explain what it means, okay? So 1 for 1 basically means the children are independent, and 1 for all means they're collaborating. So if one of them fails, you have to restart all of them. So you have this hierarchy, and each supervisor observes the children below it, the workers. Okay? So the 2 basic strategies are 1 for 1 and 1 for all. If any child dies on 1 for 1, it is restarted automatically by the supervisor with a consistent state, and the others are not affected. This happens when the children are doing independent things. You do that. And 1 for all means if any child dies, all the children are restarted because they are working together in a consistent state. So this uses the stable storage when you restart to put everything in consistent state. And there's actually 2 more strategies. So the 1 for 1 and 1 for all are shown in the picture. Okay. There's another one. Rest for 1 is if there's a sequential dependency. If the child fails, crashes, all the children that are started after are restarted because there's a sequential dependency. Maybe this worker has created like subcontracted things to others. So if this one dies, all the subcontractors have to be restarted, but not the previous ones. Okay, so that's rest for 1. And simple 1 for 1 is a dynamic version of 1 for 1, where you can create new children and stop new children dynamically during execution. So really, you have a bunch of independent processes that you can always start and stop. So this is a more dynamic version of the 1 for 1. Okay? So that's the idea. So you get the idea. But I'm going to show you the code of a supervisor now. And we'll go through the code in detail. This is a very simple supervisor, but it supervises. It does the following thing. So you have a supervisor with children. If the child terminates abnormally, it is just restarted. So it's like 1 for 1. If it terminates normally, it's removed from the supervision tree, so nothing else happens. So there's no further action. Nothing happens to the others. And if you stop the supervisor, you say, I want to stop the supervisor, it basically stops the whole application. All the children are terminated. Okay? So that's a very simple supervisor, and of course you can do much more sophisticated stuff. This supervisor assumes that nothing abnormal happens when the supervisor is starting up the children, and so the real supervisor has to do that a little bit more carefully. If the supervisor cannot start up normally, the whole startup is aborted. So that means that the supervisor could not start. So it only works if the supervisor can actually start the children. Okay? And each child is started by calling a function, an Erlang function called apply, where you have the module, a function, and the arguments. So this function is the one that actually creates and links the child to the parent. Okay? Okay? And we use linking for this. Remember, all linked processes, when the supervisor terminates, the linked processes will receive an exit. Okay? So this example is taken from a book called Designing for Scalability with Erlang OTP by Francesco Cesarini and Steve Vinosky. This is a really good book. And I'm only giving a small piece. It has many, many code examples and a lot of very good explanation of how everything works, the philosophy, how everything fits together. So if you want one book on really understanding how Erlang does everything, this is probably the best book to take for that. Okay? So I know Francesco, and he will be very happy that I'm complimenting his book. So here's the code. This is the complete code, and I'll explain how it works. This is a module, I call it My Supervisor. It has three calls, three functions that are exported. Start, which starts up all the children. Initialize, init, which initializes the loop. Normally you don't need to call this one, but it's also exported, just in case. And this one is the stop. Okay. So how does it work? You start up the supervisor. You give it a name. The name is registered. I didn't refresh, but remember, register is a way to give a name to a process, like an atom. And I will now create a new process. And this question module is a macro. It basically is just the name of the module. So it will be my supervisor, and it will start a process and call init. With the argument is the list of child specifications. Okay? So when you start it up, it starts this, and then this one returns OK. And PID is basically the actual supervisor process. Okay? Now init, first of all, it sets the trap exit flag to true. Remember, this means that the supervisor will not fail but receive messages. And then it starts this loop. So it's like a server loop. This is the loop here. I'll explain in a minute. And first it calls the function start children. So start children here. What it does is, so this is a very compact kind of Erlang code. This is a list comprehension. This will take this list here, child spec list. It will create a new list. For each element of child spec list, it will do something. So child spec list is a list of tuples that are triples, module, function, and argument. And this one will actually this function will create a child. And here I have a tuple, so the brace is a tuple. So I'm creating a list, so the bracket is a list. I'm creating a list with two element tuples. The first element, first I start the child by calling apply. This one will return OK PID. But I only need the PID, so I'm taking the second element of this tuple, element 2. And then I also have MFA in this tuple here, because I need this if I want to restart the children. Okay, so I have a list of tuples which have two elements. The first element is the PID of the running child, and the second element is the original child specification. Okay, so that's all the children are now started, and this function will actually spawn and link. So this is child specification. All these children will be linked to the process that's doing this, so the supervisor. Okay? And then this is the loop. So a supervisor, it's kind of like a server. It handles messages coming in. And what are the messages? Well, the messages are the exit messages from the children. Okay? So there's two exit messages. Exit PID normal and exit PID with some reason that's not normal. So this normal is an atom, so this one will match first. So if a child terminates normally, then the supervisor will automatically receive this because of the linking. And all it does is it removes that child from child list. So the loop has an argument, which is actually the list of PIDs, or actually these tuples of the children it's supervising. So if the child terminates normally, it just removes it. It uses this Erlang function key delete, which I'm not going to explain. You can imagine how it works. It will basically remove the element from the list. Okay? So child list gets smaller. That's this one. Second one, if the child crashes, any kind of failure, it does runtime error, whatever, then you get this message, and reason will be different from normal. What do you do then? So the child has crashed. Remember, Erlang has this let it crash philosophy. Any failure, you crash. So we know the child has crashed. So we restart the child. Here, we have the PID in the child list. So here's the function restart child. So basically, you looked up. So PID is a constant. It's the ID of the child. So we look up the child in here from this one, and we create a new child. This one will have a new PID. Yeah? Whenever you create a process, it's a new one. And then we call p replace, which replaces PID entry by this one. So remember, child list has these tuples, the PID and the MFA, which is for restarting it. So it replaces the PID by a new PID. So this has basically restarted the child, and it has put the PID of the new child in the list. Okay? And now I'm calling the recursively loop with the new child list, okay, which is returned by restart child. So that's very easy, yeah? And the final message is stop. But this message comes from the outside. This should be lowercase s. This comes from the outside. This will terminate. So I can stop the supervisor, all of the children at once from the outside. So basically, the termination, it will do a for each. So it will go through all elements, all children, and it will basically kill them. Actually, that's very murderous, huh? You're killing children here. Actually, this is kind of funny because the book that I just mentioned, it has a box saying, be careful, people don't like when you say you're going to kill children, so don't say that, okay? But that was the original terminology. Erlang was done like in 1988, and they were not so politically correct in those days, okay? So this is the full code of the supervisor. So you see how it works, huh? And so I expect you to understand how this code works, huh? So this code is actually not so complicated, right? Note that you have linking, you have higher order, and you have this notion of separate processes with message passing. You can do this fairly simply, huh? You see that, huh? So I've added a slide. I'm going to put this new slide on the Moodle with some explanation, because I realized that maybe this is a little bit complicated to understand like that. It has things in it. So I added a slide. So the question module is just a macro. So Erlang has this macro system. Value is the name of the current module. The list comprehension is something that's used here. So Erlang has this concept of a list comprehension, where you can create lists from other lists, okay? And I'm explaining here what apply does, what element 2 does, and the function f, this is the child specification. It spawns the child and immediately links it to the parent. So spawn and link. Here's what it does. Okay? And the supervisor loops. So this loop function here. So it kind of looks like a server. Huh? It has a loop, like a server loop, because it's always doing something and waiting for things. And the argument is a list of tuples. So these are pairs. The running child, PID, and the module function argument, which you need to restart the child. Okay? So you see how that works? So this seems very straightforward, right? Doesn't it? Simple. But it's very powerful. This, what I'm just showing you here, is the foundation of why Erlang is so powerful for building robust systems. Okay? Let it crash, no sharing, and supervisors. Okay. So just to summarize a little bit, this, what I showed you is the generic part. I didn't actually show you what the children are doing, the code inside the children. I didn't actually show you anything. But in the book by Cesarini and Vinosky, they give examples of what the children could be doing. You might, for example, it might be doing the frequency allocation, okay? So you spawn the supervisor in the generic part, you start children, you monitor, restart, clean up. So this is all generic stuff. And the specific child dependencies, maybe the children depend on each other. That might actually affect the supervisor. What children, okay? So there's a generic part and a specific part, okay? So that's how the supervisor works. And this gives you a simple example of a supervisor. And the real supervisor just builds on this, and it does much more than this, but it's just as easy to use, okay? Now, I mentioned the second part of the supervision in Erlang, which is the stable storage. So this is done here. You restart the children. You have to restart it. Here it's nothing special. You have arguments A. But really, in real life, the children might actually be doing something in the real world. It might have some state. Maybe it's doing like phone connection, it's spending money or whatever. So there's some stable storage. So it's not enough just to restart with the initial arguments. And so then the second part of supervisors is the stable storage. And Erlang has a really good support for that. The basic, simple support is called ETS, Erlang Term Storage. This is the very fast stable storage. When a process fails, the ETS does not disappear. The ETS is like it's like the global, in some sense, it's kind of like global variables that are stable. It's in memory, so it's not in disk. So it's not as reliable as disk, but it's extremely fast. So this is the fastest version. And then Erlang has more slower and more reliable versions. So the ETS, and then you have disk ETS, DDEX, and then you have Mnesia, which is a full-fledged transactional database. But here I just mentioned ETS because it's the one that it's used most of the time first. Okay? So the ETS is in memory. When the process crashes, these ETS values are unaffected. And you can, actually the ETS tables are also managed. Okay? So it's typically managed by the supervisor, not by the child process. Because when the supervisor stops, then the ETS table is deleted. So there's no garbage collection of ETS tables. It's managed by the supervisor. okay? Not by the child process, okay? And so this is the second part of the supervision, huh? Supervisor and stable storage, okay? Okay. Now let's take a step back and compare this. So later I'll talk about industrial use of Erlang, but right now let's just think about it a little bit. So supervisors handle the errors. When a child process has an error, it is designed to immediately crash. It does not try to fix the problem. Remember the example of the surgeon who did the appendix, that removed his appendix on himself. The child process does not do that. That's very bad. You don't want to do that. This child process immediately crashes and the supervisor does the rest. So the child will not try to fix the errors. So all error conditions are mapped to one failure action, which is to crash. Okay? So no defensive programming. It used to be that when you write programs, it was kind of recommended to do defensive programming, which is putting checks. The children will be checking a lot of things. And there's actually some studies. Okay? So for example, here's one done where you compare a system which is done in C++ and in Erlang, so the same functionality. So this is an example done at Motorola, okay, two-way radio communication. So if you look at the Erlang implementation, it has 85% less code, which means it's like 1/6 of the size. 27% of the C++ code was defensive, was error handling, whereas only 1% of the Erlang code mapping. Okay, so typical studies, they show like the same results. So for the same kind of fault tolerance, the Erlang code tends to be a lot smaller. You can say, so Ericsson did a study here, which is Plex, which is a kind of imperative language, and Erlang, local kind of Ericsson language. And they also saw enormous increase, 10-fold decrease in the code size. So you can say, wow, that's amazing. Is it really true? Why isn't everybody using Erlang if this is true? Actually, Erlang is used a lot. And I will show in a minute that gaming is an area where Erlang is used a lot. It's used a lot when you really need the fault tolerance. So it is, the answer is it actually is used a lot, okay? So that is the conclusion for the first part. So from last week and this week, I showed you the Erlang plus OTP, the behaviors, the primitives. So it's two levels, There's the primitives, and then there's the behaviors. And I showed you the primitives because this is a course where I want you to understand the magic. But a programmer will only see the behaviors normally, okay? So a lot of effort goes into the design and the improvement of these behaviors. So all of the work of the OTP team, most of it was in building the behaviors, okay? Server, finite state machine, event handler, supervisor trees, and the stable storage is a very important part. The ETS, DETS, and Venetian, okay? So this is the conclusion. So you have here a system with the primitives and the high-level concepts for building concurrent distributed systems, okay? So that's the first part of today's lecture. The second part will be explaining, I will give you an industrial talk. So this is important. This is a really a real industrial experience. Okay. So there's many talks on Erlang. So there's a lot of industrial conferences There's a conference called CodeBeam, which is like twice a year. There's one in Europe and one in the United States. And so this is a talk I chose. This was in a conference called Erlang Factory, held in London in 2011. And it's called Erlang and First-Person Shooters. Okay? And so this is by a guy from a company, Malcolm Dowes, from a company called Demonware in Ireland. Okay? But maybe, and this gives a lot of industrial experience. Maybe I can break now, and after the break, I'll show you, really get into the nitty-gritty of industrial application. Let me start again. This is a talk. This was what I'm going to present now. Was a keynote talk done by an engineer, Malcolm Dowes, at a company called Demonware, which is based in Dublin, Ireland, in 2011 in one of the main airline conferences. In those days it was called Airline Factory, and this was in London. Okay. Tens of millions of Call of Duty Black Ops fans load test Erlang. So this guy is giving his industrial experience, and in several parts. First, the history of Demonware. How did this company start? How did they get into Erlang? What are they doing? So that's really interesting if any of you want to start a company, to see the experience of these guys. The second part is how they use Erlang now. Now, this is 2011, it's still true today, and what we have learned. So the lessons learned, mistakes they made and fixed, and things they would like to add, and what are the nice things, and what do they especially like about Erlang. Okay, so both the good and the bad. Okay, Demonware is a company that supports games, and they do a number of things. Middleware for client-to-client game state transport. So you have two gamers exchanging data. You have encryption. You have NAT traversal. These slides are on the Moodle, and I've added some text in red on the bottom to explain some of the terminology that maybe you might not be always familiar with. So a NAT is a network address translator, is basically changes the IP address from inside the company or the house to outside, because they maybe don't use the same IP space, and so you have to manage that. Also, connection management, peer-to-peer. Peer-to-peer is that the clients are talking directly without contacting a server. But you also have star topology, a star, where you have one server in the middle and all the clients are talking to the server, even when they send messages to each other. So you have both of these things. So Demonware supports that. That's one thing they do. They also they basically support everything that is done that is outside the actual game engine. So you know a game has some kind of a physics engine inside that models the real world to some degree of accuracy and has all the game logic, and it's very highly optimized. So this part is not written in Erlang. This is a very specialized high-performance kind of engine. But everything around that is what Demonware does. And this is called the lobby servers. So before getting in, you go to the lobby server. So things called matchmaking, leaderboards, statistics, messaging, audio, video, websites, teams, and also things against cheating. So the lobby servers is what allows players to meet, arrange the games, as opposed to the game servers that actually run the game. So you basically have lobby servers, and in the center you have the game servers. Okay? So all the stuff around the game servers is what Demonware does. Okay, so how was this company started? It was founded in 2003, developing middleware for games. So basically a bunch of developer students actually. 2005, they started hosting lobby servers. In 2007, they switched to using Erlang, which I will explain how that happened. They were then acquired by Activision Blizzard. And in 2011, they're one of the world's largest online game service providers. That doesn't mean much in terms of employees. They have 60 employees, offices in Dublin and Vancouver. Okay. This is some games that use them. You may have used some of these games. I don't know. Call of Duty. You've heard of Call of Duty, I guess, huh? So there's most of the Call of Duty games and also other ones are using software from Demonware. So there's a lot of support for games and many more. So Demonware is really a big company for support. All the things that go around the game engine, okay? So that's Demonware. So what do they support? The full online infrastructure for Call of Duty Black Ops. In 2011, this was the world's best-selling game. 4 of the top 10 games on Xbox Live. Over 2 million concurrent users. It's not bad for a piece of software. 150 million registered users, and it's cross-platform. So a bunch of hardware, Xbox, PS3 in those days, the Wii in those days. Okay? Coming soon, 3DS, etc. But that is still going on today. Huh? How did they get into Erlang? Okay, so that's an interesting story. So here it's very interesting, maybe for you guys. In 2003, it was founded by students from Trinity College Dublin. Okay, so you can see that this was a bunch of students. They wanted to sell client-side networking middleware to game studios. They thought, we can build support for games. 1 year later, it didn't work out so well. Lots of polite interest. Polite interest means, oh yeah, looks very interesting, goodbye. A few customers. Okay, but the game studios wanted online servers, they didn't want middleware. So they started creating this lobby services platform. Okay, Xbox and PlayStation. Okay, so Xbox Live was kind of the standard in those days. So they started by using C++. Okay, and MySQL. So MySQL is a relational database management system, open source, very popular. Okay, so they made a C++ server, kind of regular, single-threaded. They created sub-process per service, and the application logic was in C++. They used MySQL. Okay, now this was their first thing, so this was actually not very good. One OS process per connected user is not very good. Huh? So you have like 80 concurrent users maximum. So, but the first game that they connected it to did not have so many users. So also C++ crashes a lot if the code is immature. So you need to do a lot of testing and debugging and testing and debugging. So it crashes if the code is immature, and the code was immature, and it crashed a lot. Okay, so this was their first thing. But then they did better. They put Python in the middle. They rewrote all the C++ logic in Python. They maintain a pool of OS processes, a core server in C++. Now they're able to handle thousands of concurrent connections. They encrypt, decrypt, dispatch. They have messages, asynchronous messages. They even have some cheat detection licenses, duplicate login, connection. But the code was very complicated. So C++ is the wrong language for concurrency in their experience. It was very hard. The code was very complicated, impossible to maintain, poor error handling, debugging was very hard, metric scalability was very hard. Whenever they had to change the configuration, they had to disconnect all the users. So note that in Erlang, you wouldn't have to do that, okay? So problems. problems. Okay. So, this is now in 2007. One of the former developers, just by some kind of an idea, rewrote the server in Erlang just to see what it is, okay? Because the server was in C++. And after a few weeks, he got this prototype and it was running. Oh, and it looked nice. And then they said, hey, let's turn this into something real. And they took them 4 months of development to turn it into something that was able to go live. So in mid-2007, it was used for the first time. So you see how it went? It's just somebody said, well, we're having so many problems in C++, let's just try. Erlang seems to be maybe better, we'll try it. Okay, so they tried, and in a couple of months, they actually got something nice. Okay, so some of the improvements, so it didn't crash. That was amazing. The configuration was easier. They could reconfigure everything without affecting the clients. Amazing, huh? Hot code. You can run it, reconfigure, and the clients don't see anything. The logging administration is better, faster to develop, far fewer lines of code. So this is the industrial guy who's talking here, huh? Okay, now 2007. Okay, still a very small company. They have now a bunch of customers. So they have this nice lobby server. Now it's written in Erlang, it's working nicely. They have some customers, nice customers, Activision, Ubisoft, etc. Activision liked it and acquired them. They had a few big games. You may know some of these. But still no monster blockbuster. Okay, so in 2007, they had games with 20,000 concurrent users. Not bad, but it's not the huge blockbuster yet. And it's still kind of a tiny company. 11 developers, 3 persons handling the operations, and 3 managers. That's kind of small, huh? So this was, but still they were doing stuff. And then they get a real challenge. In 2007, a blockbuster arrives. This was Call of Duty 4, okay? 2007. You may remember it, I don't know. This was the most popular game on the PS3 in those days. But for them, it was lots of pain and suffering. So they have the system with 20,000 and it was working. And then this huge thing happens. And the number of users was always growing. 5 months, always growing for 5 months. New bottlenecks every weekend. Things were going wrong. They had bottlenecks to solve. Lots of outages and late nights. So this was like growing up for the company. Okay? They had to grow up. So before that it was a small company, 20,000. And now, all of a sudden, ooh, they're in the big leagues, okay? And so Erlang actually caused few issues. They were able to scale up, and they kept all the Erlang code. So without the switch to Erlang, the crisis could have been a real disaster. But they actually survived this crisis, and actually got bigger and bigger. Okay, continual growth. From 20,000 to 2.5 million concurrent users, that's a lot, okay? The number of requests per second on their system, from 500 to 50,000. The number of servers, so you have millions of users, but you have a bunch of servers, okay? The original, they had 50 servers. Now they have 1,850 servers talking to each other. That's a big system, okay? And then the company grew in staff from 17 people to 60 people. Still not that much, huh? For something like this. Spread evenly between Vancouver and Dublin. So Canada, North America, and Europe. Also, they grew in competence. They really matured. They added many new features, services. In 2010, there was the Black Ops launch. This was an enormous thing, so it was a lot of work for them. Okay, so the core of this thing is Erlang with Python and MySQL, but many other pieces. So not just that, there's a lot of things, okay, there. So how do they use Erlang? So now you see kind of the growth. You see these are a real company, yeah? And you see kind of how they grew from just a few students doing something to a real company playing in the big leagues, okay? So how do they use Erlang? Okay. Erlang is their core server, so it controls Python. So there's lots of Python scripts. It manages hundreds of thousands of concurrent TCP connections. It schedules tasks for the Python code. It gathers metrics, so statistics on maybe there's bottlenecks, so the system has to measure itself. It has a presence server, so this is a kind of database. This is using Manesia. Remember that I mentioned this in Erlang, a fragmented version of Manesia, which means it has some different servers. And everything is done using message passing. Okay. They also did other things with Erlang. They made other kinds of servers for lots of extra kinds of things. Transient in-game data through servers, testing bandwidth, leaderboards, ranking in real time. So basically the Erlang was used for all the concurrency and gluing the sequential code together. And the sequential code could be written in Python, for example, or other languages. Okay? So this was basically the core server controlling the concurrency. Okay? So how do they do some of the things? So the TCP connections, the task scheduling, for each connected user, there are two Erlang processes. So remember, we have the supervisor with all the workers. So you have two processes that are handling each connected user, and they use a simple one-for-one, which means you can start and stop them individually. And they delegate work. These processes delegate work to Python, actual operating system processes. And there's a large supervision tree here. They have dedicated task queues, so you have lots of things going on. And you can restart or update the Python code without affecting users. So this is pretty nice, and it's all controlled using Erlang. Okay. They also have periodic tasks using timer. So this is the kind of structure per user, how it's done. They did something called a presence server. This is something that you need to ensure that a user cannot be logged in twice, and that there's no duplicate license keys like on PCs. And who is connected? So this provides a snapshot, a concurrent distributed snapshot of who is connected. It also supports all the in-game messaging. Okay? This is using an Erlang library called fragmented Manesia, where the Manesia is existing on multiple nodes. So this one actually scales very nicely and robust. And so they have clusters which are collections of computing nodes that are tightly coupled. So their biggest cluster was 16 core Dells. So this thing, more than 60. This thing has more than 1,000 cores. Okay, that's pretty big. The present server. They also do metrics. In a big system like this, the system is always measuring itself and seeing whether there's bottlenecks, or you have to keep track of everything. And Erlang has this SNMP, so network monitoring protocol libraries, so they're used. So they monitor the users, requests per second, request times, queuing times, logins, logouts per second, why the users get disconnected or thrown out. So, and then they make these real-time graphs. And the most used thing is an ETS. Remember, the ETS is like global variables that you can update very fast, stable in memory. ETS update counter. So they're counting. Tuck, 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 tuck. So they're calling ETS update counter a lot. So this basic little Erlang function is really called a lot, millions of times. Okay? And also, between all the clusters, they're combining the metrics to generate overall metrics. So cross-cluster metrics. Okay? So here on the bottom you can see I add sometimes little red text stuff. Simple network monitoring protocol. SNMP. Okay. Each game has a different configuration. It can be very complicated. All different pieces have to be connected together in the right way. And so the Erlang code handles all this game configuration with all the different options, the defaults, instantiation, inheritance if you want to connect one configuration depending on another one, upgrades between clusters, rollback on failure. So this is nice. So rollback on failure, when there's a failure, the system goes back to a previous consistent state. Okay? And something called Puppet integration. Puppet integration, so there's a lot of kind of jargon buzzwords in the industry. Puppet integration is an approach for delivering and running the software the same no matter where it runs. Okay? So it's kind of independent of where it's running. Okay? And a lot of effort to make this as simple as possible. Usually configuration is one of the hardest things. Okay? So this was something they worked a lot on. Okay? There was also web interfaces, lots of web interfaces. Erlang has this generic web server called YAWS, yet another web server. And they use that one a lot, which has a very high concurrency. You can have many tens of thousands. You saw the graph in the beginning last week. For the web console, this is for the developers. Okay? And live debugging, to debug while the game is running. You can also do development, web services. You can control the game, message of the day. You can remotely see how popular game features are. You can control the clusters remotely. So there's lots of web interfaces for controlling, for debugging, for developing, okay? And they have a lot of services related to the game. One of the things people like is the leaderboards. So giving the ranking of the users. So these are huge, these are leaderboards with 15 million users ranked in real time. So this is using the ETS, stable storage, and a kind of a tree, a special kind of tree managing module. Okay, so that a data structure that lets you kind of rank things and find out which is the best dynamically. Okay. Also, they have key value store. A key value store is like a database. It's like a hash table where you put things in there with a key and any kind of value, so you can store and update. This, they built it on top of ETS. So this is like a very simple database. Huh? And this lets you do things like grouping the users, keeping little groups, managing chat channels, presence information. So it's like a simple, very fast database built on ETS. Okay? So a key value store is like a hash table, table of values indexed by key. GB trees are general balanced tree modules. So this is a way of managing a large amount of data organized as a tree that is dynamically balanced, keeping so you can always know which are the best ones. Okay, so this is a module of Erlang. Other things they did was bandwidth testing, UDP packet blast. It's a nice way of calling it. You send huge number of packets, throw them at an Erlang server and see what happens. and the client can get the estimate of the bandwidth. Okay, so that's services they did. Okay, now what lessons they learned, so you can see kind of what they're doing with Erlang. So what lessons they learn about Erlang? Okay, so this kind of reviews the stuff we saw about Erlang. The core data types, records, not tuples, binaries, bit strings, we didn't use them so much. And the refs, the unique values, the LO list, special kind of list data type. Second, think functionally, think concurrently. You have to think concurrently, so forget all the sequential stuff. Tail recursion, functional data structure, higher order, so they use lots of higher order. New processes really are that cheap. So that's something people who are used to programming Java don't really believe, that a process can be extremely cheap, and they really are, he says. Okay? So simple things can go a long way. Okay? Then you have a couple of Erlang features here. So IO list, so this is IO list, is a list whose elements are integers, binaries, or other IO lists. A kernel poll is the kernel pulling the file descriptors. So this increases I/O performance with many descriptors. So it's an operating system technique. Okay. So don't forget to read the red stuff underneath. Okay. Now OTP. This is the behaviors. What they find is use it. Okay. Religiously means only it. And use gen servers, use the supervisors, avoid touching receive and send. Don't actually send messages yourself. Do everything with behaviors. Don't do spawn yourself. Spawn link, which spawns and makes the link at the same time. Don't call trap exit. All of that is done inside the behavior. So really use the high level stuff, okay? Also, split reused components into their own OTP applications. If you have pieces of a system that is reused, turn it into an application, and OTP supports applications, okay? Also, the modules. Erlang is organized with modules. Keep them small. Keep them non-side effecting. They don't have side effects. They don't update global state. Keep them sequential. The concurrency is in the behavior, okay? So the modules can be OTP behavior modules, they're the specific modules, or simple, non-side affecting sequential modules. So all the concurrency, all the fault tolerance is done in the behaviors. Yeah?
Can you remind me what OTP stands for?
Well, it's the name that Ericsson gave to the platform. It's called Open Telecommunications Platform, because it's basically open source. So this is the name they gave when they made public release. So this is all the libraries, not just the language, but all the libraries and systems. But they call it the Open Telecom Platform, because the original was for telecom. And then there's another lesson, very general lesson, which is the KISS principle. This is a very important principle. Keep it simple, stupid. A slogan for system designers. Don't do things in a complicated way. Keep things simple. For example, avoid internode dependencies. Dependencies are bad. That's general saying, not just Erlang. Of course, Erlang makes it easy to have connections between nodes. You just have PID of another one. Or the node here is the computers, huh? A single computer and a network of computers. They shouldn't depend on each other. So the no sharing principle, you have to use it also, not just let Erlang use it, you use it, okay? Avoid nodes with special responsibilities. Everything should be kind of decentralized, okay? And you should expect that sometimes you have high latency. Don't expect things always to run fast. Expect problems, okay? Internode network issues. Expect problems because of dependencies. Complex inter-process dependencies, very bad. Be very afraid of processes which rely on each other. You shouldn't have a bunch of processes all connected. That's very, very bad, okay? And casts instead of calls. Remember I mentioned cast and call? Call is round trip, You send and you receive. But a call is kind of a dependency, yeah? You call and you wait for the result. So you're dependent on the other guy. So it's actually a dependency, a call. So what they find, these guys from Demonware, is you want to avoid that. Even a simple call can be nasty. Because you wait for a result. What if no result comes? What if the other guy fails? Or something happens, or there's a delay. So waiting for something is very bad. Casts, they don't wait. Casts, you just send it and forget. So casts actually are the way to do it. So your system should be asynchronous. Don't wait, okay? The calls are waiting. This is very simple. You think, why is this a problem? It's so simple, it's a call. Even something so simple is a problem. Okay? Because here, I mean, these guys have millions of users, huh? Even small problems can go into big problems, huh? Okay, another lesson, bottleneck processes. Now, we're talking millions of users concurrently, and there's lots of processes handling this. What if one process is like a bottleneck? It receives many, many, many messages. Huge number. So it is slowing everything down. Okay? That you want to avoid it. Avoid the bottlenecks. So you create a pool. Instead of one, you have several, and each one handles part of some of the messages. Also, make sure these processes are not actually doing so much work. Because if they do work and they have many messages, not good. Okay? And manually purging the message queue. So if there's a lot of messages coming in, sometimes you can get rid of some of them. Okay? So that's one thing. The second one, some processes do real work. They actually have to do work. Well, when it's doing work, leave it alone. Don't send messages to processes that are doing work. Seems very simple, okay? And also, it decides when it wants to do more. Don't overload somebody with work, but when that person is finished, that person, the process is finished, it asks for more work. So you have a pull, not a push approach, but pull approach. If you build a big system, then each process will ask for work, and you don't actually push work. Don't send work onto processes, but wait for the processes to ask for work. And that will let the system kind of balance itself. That really is important for big systems, okay? Okay? And some bottleneck processes are logging, a log process. So logging is important because you want to keep track of what happens. So the log puts all the things that are happening to trace in a stable storage. But if there's one process doing that, that process will get a lot of messages. So you don't want one process doing the logging, or metrics. You want to keep track of performance. Also, if there's one process doing that, it will be overloaded. So these guys are important, but they tend to get overloaded. Okay? Not important lesson. Okay, the stable storage. So ETS, Erlang term storage. The lesson is, ETS is great. Use ETS. It's the standard solution for most of your in-memory storage. It's blisteringly fast. Industrial people love to use the word blistering. Okay, blisteringly fast. So fast that you get blisters. I don't know. Okay, it's also automatically cleaned up. Remember I said it's connected to the supervisor, so it's actually deleted when you don't need it. Okay? It avoids single process bottlenecks because the ETS can be accessed by many processes. Okay? Okay, no monster crash dump. So a crash dump is something that happens when the system crashes and you have a huge dump of everything what's in memory. If you use ETS, then you don't have to do that so much. All the stuff is in the ETS. Okay? So use ETS, but ETS has limitations. It's just variables that you update on ETS. It's not a transactional database. Manesia is a transactional database in Erlang, so don't reinvent Manesia. If you need transactions, use Manesia, otherwise use ETS. Also, what if you have a distributed system? So ETS is on a single node. What if I have multiple nodes, multiple computers, that have to store things? I have to make copies of the ETS tables. So you have to worry a little bit about that, so that's a little bit harder. But the lesson is use ETS. Second lesson is Manesia. So I said there's like layers of database in Erlang, starting with ETS and then disk ETS and then Manesia. So the top one, ETS, is fast but very primitive. The other one is slow but very sophisticated. So Manesia is a very powerful database. It's distributed, it handles fragmentation, atomicity, it's transactional. It's a real strong database and it stores Erlang's data. And this is one of the main reasons they moved to Erlang. They really liked Manesia. But Manesia is complex. So this is a really complicated thing. Big databases tend to be complicated. A lot of subtle custom code. It handles partitioning. It handles node death. When a node crashes. It handles fragment distribution. How do you spread the database over multiple nodes? So Manesia is kind of like a traditional relational database management system. It's powerful, it's fully featured, but it's complicated. And this is the industry guy. You will swear and pull your hair out. So I don't know if he was bald or something, but he pulls his hair out. But ETS is simple, but it's maybe sometimes too simple. So you have this kind of dilemma. Do you build something on top of ETS or do you use Manesia? Okay. So the idea is use Manesia, but carefully. Okay. Okay. Testing, very important. Automated tests. So you see that already here. So this is the industry guy saying it. They use eUnit, which is the Erlang unit testing full clusters. A system for stubbing out modules. Basically, making modules turn into, I'm not sure exactly what that means. Stubbing out, stubs. Fault injection, killing random Erlang processes. This is very nice. You have this big running system with lots of Erlang processes. Just randomly kill one. Or more of them. Just start killing them and see what happens. That's a really nice way of testing out. Randomly kill the processes in testing, and this is called fault injection, because something else almost certainly will. If you do that, and if it keeps on working, then you're really good, huh? Okay. Also, pay attention to dialyzer and fprof. So dialyzer and fprof are tools for Erlang for debugging, profiling, finding bugs. And finally, end-to-end load test. You simulate 2 million users. So the test is this huge thing where they have 2 million simulated users pounding on the system. Okay? That's very important. Okay? So these guys, you see, they're very serious. Fault injection, heavy-duty end-to-end load testing. Okay? And a few other lessons. Keep your clusters apart. This is part of low dependencies. Different local area networks, different cookies. Keep your clusters apart. Beware of sharing cores with other OS processes. If I have a multi-core, and this core, and there's many OS processes on there, problem, don't do that. Okay? Also process priorities. 10,000 relatively unimportant processes, slightly inefficient, will clobber, will kill one vital process. So a large number of unimportant, low priority can actually affect an important process. So be very careful about that. Also, they talk about the hot swaps and the code replacement. So we saw that, the primitives for that. Amazing, but often more effort than it's worth. Don't do it all the time. Do it rarely. So don't be too enthusiastic about it. So don't use it so much. And then things like kill switches, metrics graphs. Okay? So a kill switch is a mechanism that's used to shut something down in case of an emergency. So if something is going wrong, just shut it down. Okay? Lots of helper tools, remote shells for looking for debugging. So this is all the industrial stuff. So here you're really getting some real industrial lessons. Finally, kind of a political lesson, be polite. So Erlang is actually a small part of Demonware. It's all the concurrency is done. So just 3 or 4 Erlang developers are doing all this concurrency stuff. All the other developers are doing Python and C++ and other things. So your coworkers are not all Erlang fanboys. They don't care about Erlang like you do. Don't force the user of your software to use Erlang syntax, to read Erlang crash dumps, have to understand Erlang code. So this is very general. Don't force people to do all your internal stuff. Okay? Either you convert them all, or you say, well, it's a niche language. So Erlang is kind of a niche language. It's used for a small part, but very important part. The concurrency, the fault tolerance. But that's actually, in terms of lines of code, it's only a small part, even though it's important. So be polite, because it's only one piece. Okay. So that's the lessons. Now they also have things they want to see in Erlang. Okay. Some things we'd love to see. So these guys are really industrial users, and they want things. They want things that didn't exist. Maybe some of them have been added since 2011. They want improvements in Malaysia. Network outages, node crashes. Maybe combine Malaysia with Cassandra. So Cassandra is another database, not Erlang 1, but has eventual consistency and has good support for node crashes. So they want eventual consistency, automatic rebalancing, and then they understand there's something called the cap theorem, which maybe you have not heard of. Has anyone heard of the cap theorem? No? No, the cap theorem is a very important result in distributed systems, that there are 3 properties that you want. Consistency, that all your data is consistent with each other in a big distributed system. Availability, which means that whenever you make a request, the system is working and answers your request in a reasonable time. And also partition tolerance. If your system breaks into 2, if the network breaks, you want your system to keep working. Now, these 3 properties are all 3 very important, but you can prove that it's impossible to have all 3 of them at the same time. If you want a system that is consistent, available, and partition tolerant, it's impossible. That's known as the CAP theorem. That was proven in 2002. You can have two of them. If I have partition tolerance and availability, but then maybe the system will be inconsistent. Or I can have partition tolerance and consistency, but maybe sometimes the system will not be able to reply when I make a request, so it won't be available. So available is a formal concept. Availability means that if I make a request, the answer will come within a reasonable time. Okay? So of course they say, we want Manisha to be better, but we know there's no magic bullet. Okay? The CAP theorem is a general theorem that works for any distributed system. Okay? What else do they want? Automatic cleanup logic. Manisha data right now is not connected to the process responsible. So if that process dies, the Manisha data should be cleaned up. Okay? So they kind of want that, want kind of extensions, or old and new incarnations of a node. If the node crashes and you have a new version, the two have different data, okay? And you have to clean up the data from the old one, which might be spread around. Maybe you want that to be more automatic, okay? Okay, here is a very nice slide. They want improvements in OTP. This is actually what I like very much. Receive, send, link, spawn is like assembly language. It's very primitive. Okay, it's the primitives. So you don't want to use it. But you still have to know how it works, but you don't use it. So what they want is more flexible supervision trees. Handcrafted dependencies. They want better ways. One for one, rest for one is kind of too primitive sometimes. They want better restart. Remember I said the thing restarts a certain number of times? They want improvements, like exponential backoff. So exponential backoff means whenever you restart, you wait a little bit longer, or you multiply the time. And this can reduce congestion, okay? They want more ways. Supervised process monitoring can also be supervised, okay? They want system messages to be handled quicker. Writing well-behaved, blocking, or busy process messy. So they want a new behavior. Gen background script. Okay? So they want more from OTP. Okay? Also what they want is connecting Erlang to other languages. Erlang, for them, is not really general purpose. It's great for concurrency, and hard concurrency, but they would not use it for business logic. They would use something else. The ease of concurrency does not make up for the difficulty in interfacing with other languages. Okay? They want better interface to other language. It's just too easy to muddle through without Erlang. That means you can do all kinds of weird stuff without Erlang, and it's hard, because using Erlang is hard because of the interface. It's not the Erlang code. Okay? So, scripting, they would like more scripting to be an Erlang process. Okay? So, and then there's a couple of things, interfaces, so 2TP and J interface. Okay? Which I'm not going to say, but they want more connections with scripting kinds of things. Okay? Types. Static types, dynamic types. Maybe they want static types. Erlang is dynamically typed, so it's strong but dynamic, which means that the variables are not, types are not declared. But there's a tool called Dialyzer, which is able to do kind of a static analysis. Okay? So they maybe want more of that. They also want more dynamic features. So they want something called monkey patching. So monkey patching means you can test code that depends on global settings. So you change, so the code is there, and you can tell you have to modify these global settings to make this code to test it. But you want to do that only for the test. You don't want actually to permanently modify those global settings. So that is a technique called monkey patching, okay? So they want stuff like that, okay? So they basically want things like that. Oops. Gentler learning curve. Well, they say in Erlang, very hard things are possible, but very easy things are not easy. Moving to Erlang is a big commitment. So they want more, better guides, better documentation, improved syntax. Actually, this was maybe solved since 2011, because now there is another language called Elixir. So maybe I'll make a picture here. So Erlang has a virtual machine called the Beam, and Erlang runs on top of that. But since a couple of years, there is another language called Elixir, which was invented running on the same virtual machine. So these two are interoperable, but Elixir is more like standard Python, Ruby kind of syntax. And actually there's a large Elixir community, so the learning curve problem is kind of solved. The Erlang, a lot of Erlang people using the Beam, using fault tolerance, are using Elixir, okay, and in addition to Erlang, okay? So that's something that they want. Okay, what do they love about Erlang? It's a little nice cute cat. Pretty much everything else. Effortless concurrency. It is the complete solution for hard concurrent problems. This is the industry guy, says it. It's also open source. Everything is visible. We can look under the hood, play around. You can do remote shells, easily, lifesaver, robust and reliable. It's incredibly robust. In fact, no other system is so robust. They have these game servers running for months without crashing. That's very normal. Par for the course means it's normal. So they like that a lot. Of course, they complain also. So Black Ops, 24-hour stats, okay? Who said gamers are lazy? For the past 24 hours, all the players in Black Ops have collectively killed more than the entire population of the USA, shot 28 million enemies in the head. So this kind of statistics is maintained in Erlang. Yeah? They shelled out 16 billion euros in weapons. They stabbed 2 million enemies in the back. Okay, 24-hour stats. Okay. So, the conclusion, Erlang helps make tens of millions of gamers happier across the world, and if gamers are happy, then we are happy. So Demonware love Erlang, and then they're hiring. Okay, so this was a keynote talk at an Erlang conference. So you have a big auditorium, and there's like 500 Erlang developers there, all doing Erlang stuff. So of course, companies are always interested. Successful companies are always interested in hiring. Okay, so there you have an industrial view on Erlang. So the guy is very honest, the good and the bad, but it lets them make very complex, concurrent, robust system. Okay, so hopefully, when you guys later go into industry, maybe you take a look at something like Erlang and not just stick with C++ or Java. Okay. Okay. Let me stop there.